Hi, this is Mrs. LaBarbara. This is Physics Chapter 5, Uniform Circular Motion and Universal Gravitation Video 4. Today's topic is universal gravitation. The objectives are to know the force that causes the moon goes around Earth and the force that causes apple to fall from the tree. They are the same force. To understand the relationship between gravitational force and distance and gravitational force versus mass. To be able to apply relationships to solve problems and apply equations to solve problems. Apple, the moon, and inverse square law. So it was known that moon orbits the Earth and Earth orbits the sun. Since both the moon and the Earth moves in a circular path, they are accelerating. So what is the force that causes this acceleration? So this question has puzzled scientists for years. So according to a legend, a breakthrough came to Newton at age 24 in apple orchard in England. One apple fell on his head. So he was able to relate the cause for heavenly motion, that's the moon goes around Earth, and earthly motion, that's the apple falls from the tree. This connection led him to the notion of universal gravitation. So universal means everything. Gravitation is universal. Universal is between any two objects, between the moon and Earth, and between the apple and Earth, and it could be between apple and the moon as well. So his concept is gravitation is universal. So how did he get the relationship though? So it was known that the earthbound object accelerates toward Earth at a rate of 9.81 meters per second squared. We can use kinematics to determine that. It was also known that moon accelerates toward Earth at a rate of 0.00272 meters per second squared. We can use circular motion equations to determine that. So he compared it to accelerations. So if it's the same force, why is the acceleration are different so much? So then he compared the apple and the Earth and the moon to the Earth. What's the difference between those two? Is the distance between the moon to the Earth and apples to the center of the Earth. So it turns out the distance between the moon to the Earth is 6 times further than the distance between the apple and the Earth. And if you look at this relationship, the acceleration is 1 over 3600. 3600 is 60 squared. So the difference in the acceleration between the moon and the apple is due to the difference in the distance from the center of the Earth to the two objects. As a matter of fact, the force of gravity follows the inverse square law. So it's a distance squared, but it's inverse. So 1 over 60 squared. So here is Newton's universal gravitation. Any two bodies in the universe attract each other with a force that is directly proportional to the product of their mass and inversely proportional to the square of the distance between them. So here is any object m1 and any object m2. They are separated by the distance r. Again, this r is the distance between center to center, is not the radius. So Newton states that the force of attraction F1 and F2 are action-reaction forces, and they are always equal in magnitude. They are toward each other. And this force, we call it gravitational force. This gravitational force is directly proportional to the product of the two masses and inversely proportional to the distance between the center of the two masses. So here are the symbols and what they represent. Again, r is the distance between the center, not radius. Gravitational force is always attractive toward each other. Let's take a look at this example. The Earth and Moon are separated by a distance of 3.84 times 10 to the 8th meters. The Earth's mass is 5.98 times 10 to the 24 kilograms, and the Moon's mass is 7.35 times 10 to the 22 kilograms. The gravitational force of attraction the Earth exerts on the Moon is 2.0 times 10 to the 20 newtons toward the Earth. That's the Earth exerted on the Moon, right? What is the magnitude and direction of gravitational force of attraction that the Moon exerts on Earth? Let's draw a picture, just like we solve any problem. Here's the Earth, here's the Moon. We know the Earth exerted force on the Moon, which is toward Earth, is 2.0 times 10 to the 20 newtons toward Earth. What is the force of the Moon on Earth? Well, the Moon on the Earth, that's just reaction force. And that is the same magnitude and opposite in the direction. Because these are action-reaction forces, opposite in direction, same in magnitude. Gravitational forces are always attracted to each other. The proportion constant, that's a value of G, is determined by Cavendish. So Newton's only states that the gravitational force is directly proportional to the product of the mass, inversely proportional to the distance between the two masses. He never figured out what is proportionality. As a matter of fact, this proportionality wasn't figured out until almost 100 years later by Lord Henry Cavendish. Using a torsion balance, actually, he figured this out in his garage. So what did he do? He set two large masses apart, and he had two small masses connected in a bar that these two masses can turn. Because there is gravitational force between the small mass and the big mass, so when he put a bar here, these bars will turn. He was able to measure the angle, and through rotational kinematics, he was able to figure out the force between those two and the acceleration between those two. And through that, he figured out the proportionality. It's G. G turns out to be 6.67 times 10 to the negative 11 Newton times meter squared over kilogram squared. This G value is in your reference table. Remember, big G and little g, those are different values, represent different physical quantities. Now let's talk about the relationship between Fg versus R and Fg versus m. So the relationship between force of gravity, Fg, and the distance, that's inverse squared. That means if the distance is doubled, then the force will decrease. Inverse means decrease by 4. That's 2 squared. If distance is tripled, then the force is decreased by 3 squared. So inverse square law, the graph looks like this. It's a curve down, very similar to the inverse relationship. Now the gravitational force between the two objects is directly proportional to the product of the masses. That means if one double, Fg double. If both doubles, Fg would quadruple, becomes 2 times 2. Let's take a look at this example, relationship between quantities. Effect of mass looks at this. It's directly proportional to the product of two. So m and m, if one doubled, then force would double. If both doubles, the force becomes 2 times 2, what becomes 4F. If one doesn't change, the other one tripled, the force would triple. The force of the relationship between gravity and distance is inverse squared. So m and m, when the distance is d, is f. Now distance is doubled, force decreased by 2 squared, becomes 1/4. When distance is halved, the force will become 4 times because it's inverse squared. Now here, when both mass and the distance doubled, the force does not change because the force increased by 4 through the mass, the force decreased by 4 through distance. So 4 divided by 4 becomes F again. Calculate Fg using equations. So determine the force of gravitational attraction between the Earth and a 70-kilogram physics student if student is standing at sea level. That's the distance of the Earth radius, 6.38 times 10 to the 6 meters. By the way, this is a very important number. It would help you a lot if you remember that number. We can plug it into the equation, G times m1 times m2 divided by r squared. So you will have 686 newtons. But there is another equation. We learned gravity equals mg On Earth's surface, this G is 9.81. So we approximate 9.8, we have 686 newtons. Because this is at sea level, so we can use this equation, G equals 9.8. Okay, gravity on Earth is its weight. Gravity on anything is its weight. It's just on Earth that G, gravity, a gravitational acceleration is 9.8. We know that already. Now let's take a look at universality of gravity. So gravity is universal. That means it exerts on any two objects. You can calculate this gravity between this student and Earth, student and another student when you are 1 meters apart. It's like you're the person sitting next to you, student and physics book and student and Jupiter. By applying the equation, these are the value you should get. I highly suggest you use your calculator, see if you can figure it out. If you have trouble, please come to ask how to use calculator to figure out these problems in class. So again, gravity is a force of pulling all matters. The more matter, the more gravity. Let's take a look at our last example. So the weight of an object was determined by 5 different distances from the center of the Earth. As you can see, as distance increases, your weight decreases because it's inverse squared. So the results are shown on the table below. Position A, B, C, D. So position A represents on Earth's surface, 6.37 times 10 to the 6. Now, sometimes different reference table give you the distance a little bit different. So the one equation we saw is 6.38 times 10 to the 6 on Earth's surface. So the question is, what is the mass of the object? What's approximately the mass? So we can use Newton's law of universal gravitation. So from here, let's see m1 is the mass of the Earth. We're trying to find m2. We can solve m2. Rearrange this equation, that is mg times r squared divided by g times m1. So in this equation, m1 is the mass of the Earth. We can choose any r, so I just choose the last one. You can choose this one, then the corresponding fg has to be this. I choose last r, corresponding fg is this, 4 times 10 to the 1. What is m2? After you plug everything in the equation, I have m2 equals to 100 kilograms. You can also do in an easier way. See, this is on Earth's surface. So on Earth's surface, we have mg equals m2g. We know the value of g. That's 9.8 or 9.81. So we can use that equation. On Earth's surface is 1,000 newtons divided by 9.81. So we also get roughly 100 newtons. So that's why this number is important for you to remember. It can simplify your calculations, so you can speed up. That's it for today. Thanks for watching. See you next time.